Hi, welcome to my channel, The Machine Learning Engineer. Today we continue with another video on the series Computer Vision, and today we are going to see how to do cropping and rotating images. As usual, I have prepared an output and later on I will upload to the repository of the channel, and you will be able to download it and run it in your local environment. And as usual, I have prepared some documentation. I will explain the concepts, and later on I will do a small demonstration of how to do these two tasks with digital images. To understand the concepts, as I did in previous videos, let's go to the basics and understand what is a digital image, how it's configured or set up a digital image on the digital world, and how essentially work these transformations of the digital information. The digital image is not more than a matrix or a matrix of pixels organized in two or three dimensions, essentially three dimensions, because we had the matrix where is organized the information, the minimal information of in digital for a digital image is the pixel, and then in the way that we organize the information is in matrices. Every matrix is the representation of one channel. If we are talking about black and white images, there is only one channel. If we are talking about color images, we have three channels. This is the most general way to represent digital images. There is other standards or formats. The most general is the RGB, and the RGB is representing the images in three dimensions. One is the first one is the width, the second one is the height, and the third one is the channel. And again, depending if you are working with black and white images, you just had one image, one channel, and if you are working with color images, you have three channels, RGB, which are red, green, and blue channels. We will look at this a little bit later, how these matrices are organized, but I can anticipate a little bit. This is kind of what you had. The representation of an image. As you can see here, there is matrices, matrix of every channel. In this case is the representation of the color image, and then you have a matrix for the red channel, a matrix for the green channel, and a matrix for the blue channel. The matrix had two dimensions, are two-dimensional matrix. One dimension is the width and the other dimension is the height. Then on the every single cell in the matrix is a pixel, and this pixel is the minimum information, the minimal component or information component that we have in an image, and is always a number with data type integer 8, meaning that there is 256 possibilities from 0 to 255, and the symbol 0 always means accents of that color, and 255, this means the maximum expression or the maximum brightness of that color. When you are working with black and white images, so the 0 means black and the 255 means white, and in between 0 and 255 there is different scales of gray. When you are working with color images, you have three channels, the ones that you see here, and then on the numbers means exactly the same. 0 means absent, in this case, of color red. For example, if you are in the red color, in the red channel, and 255 meaning the brightness, the maximum intensity. of red, and the same approach for the rest. So when you had everything in zero in a pixel, so every well, I will come back later on. So again, maximum brightness for that channel is 255, no, sorry, zero. Minimum minimum in intensity or minimum brightness for that color or that channel is 255. Okay. And then on how we organize an image. So the images usually had what we know as resolution. The resolution is essentially a metric or a measure of how many pixels is this information will represent colors, and how many of these pieces of information we had per inch. The simple image, you can understand it like an image which has just simply a pixel per inch, and then on we had a square of 1 inch width and with 1 inch height, and then in you had either a tuple of one element from 0 to 255 in different scales of gray, and the whole square had the same color. And then on each you had a color image with 1 pixel per inch. You had, instead to have just one tuple with 1 element, you had a tuple with 3 elements, and every element is a number from 0 to 255 that correspond to the 3 channels that forms a color image in the digital world: the red, the green, and the blue channel. When we had, for example, like this case, 2 pixels per inch, you had 4 pixels in total, and you fill every pixel following the same approach that you use here. One element with a number of from 0 to 255. If you had a color image in this pixel, you had the information of the tripleta from with 3 channels from 0 to 255, and you can continue as more pixels per inch, as you can imagine, more resolution and more close to the reality is the image. So the final color that you see in a color image in a pixel is the combination of the three different channels, and obviously depending on the number you had more or less of one of the individual channels, of the red, of the blue, and the green. And then on moving forward, you had the other way to express the resolution, that is dot per inch. That is, you probably know more this on the when we are talking about printing. This is kind of expressing how many inks droplets are in a inch, and then on this and we know this probably more, as I mentioned, from the world of printing. And then on a printer with more resolution is the one that had more DPIs, drop per inch, or dots per inch, meaning that the printer is able to do better printing. You can translate this. This is coming in any case from the digital image world, and then on is the same concept. Here we are just simply saying we just keep the nomenclature here at 8 pixels per inch, and here we just can see 300 dpi, what is 300 dots per inch, which is equivalent to 300 pixels per inch. Here every dot is the representation of a pixel, which can be color or black and white. Here you had a description of the different channels. And as I mentioned before, how you form the colors. Red is 255 in the red channel and the other two. 00, green, similar, blue, similar. When you see this is the pixel, information that you have in a pixel, a triplex with 3 numbers. And then if the pixel is purely green, you have 02550, and if the pixel is purely red, you have 2550 and 0. Yellow, you have here the nomenclature, and here you had, for example, what means black, accent of any color, and what means white is all the pick all the elements of the triplex at the maximum brightness, at the minimum brightness, sorry, which means 255. And then on different scales of gray is also varying the pixel number in the different colors. Here you have a representation, a visual representation of the matrix that form an image of 5 pixels per inch, with the 3 matrices with the different numbers that you had in every single cell. So the pixels in this case, for example, is for the pixel in the top left corner of the image is for starting from red 564, and then on the color you can find it when you mix this color, which is the number 5 on the scales of reds, the number 6 on the scales of greens, and the number 4 of the scales of the blue. You mix them and you get the final color, and this is the one that you are going to see in this pixel. And you can apply the same formula to the rest. So now we know how this is configured, a digital image, and now we are going to see how this is represented in numbers. Let's take an image. We take an image and we read it with OpenCV. And you can see here the image is not more than, when you open it with OpenCV, you get directly let's see here, an NumPy array. NumPy is a library to work in Python with arrays of data, and then you can, when you print the shape of the array, you can see here the height of the image, the width of the image, and the number of channels. It's a 3-dimensional vector, and you can see here the printout of the. You can take the pixel 0. Sorry, no, this is not the pixel 0. The pixel 0 is this one. You had here the red color, the blue color, no, the green color, and the blue color. If we go to the image, you can see that it's very close to 255, all of them, all the channels, and you can see that match perfectly with what we had here. Here I'm going to explain you as well how you can localize a pixel in the image. The beginning of the axis coordinates is the top left corner of the image, and this is starting the axis X, the 0, and also the 0 of the axis Y. And then on moving to the right, you increase the X and move it down. From top down, you increase the Y. You want to localize a pixel which is 200x and 200y. You just go to the intersection of these 2 points, and you have here the pixel 200, 200. And similarly with the other ones. So here you can check here the axis is from 0 to something more than 1400, and here from 0 to 1000, and this perfectly matches with the shape of the image. I wanted just to show you this in a scale representation. The image is bigger. Originally here is just plotted with matplotlib, which is a plotting library also in Python. Now here in this next cell, I'm showing you a representation of the three different channels, and to do this, we just simply take the matrix. As you remember, the matrix has 3 dimensions, and here we are just taking all the red channel. So we take all the points there. When you put the semicolon in the first position of the matrix and the semicolon in the second position of the matrix, this means that we take all the cells in this for these 2 dimensions, and for the third dimension, which is the channel, we take the channel number 0, which is the red channel. Similarly, we do the same with the channel with the green channel and with the blue channel. Here we are just plotting every channel in a different image, and you can see here we are plotting as well this with a color math corresponding to the channel that we are plotting, red, green or blue, and you can see the different scales of red, blue and green according to the channel that we are plotting. The size is obviously the same because it's the same image, and you can say that the contours, everything is the same image, but we are only plotting the one individual channel. The image that you see is obviously the output of mixing up the different scales of the different colors looking at the scale from 0 to 255 in the different positions of every pixels in the image. The combination in the 00 is a combination of the color that you see here plus the color that you see here plus the color that you see here, and so on and so forth. When you do the cropping, we just simply take a vortex, the top left vortex is a position that had to be obviously inside the image. So in this case we had the X had to be 1500 maximum, and the Y had to be maximum 1000. And then on, the way that you slice is just simply slide an image, the 2 dimensions, the width and the height. You keep the 3 channels, and then on you can see here we are just simply slicing a matrix, simply NumPy slicing operation. We just take the position 540x and 385y. This is this position, and we take from 385y to 685y. This is this part. And x we take from 550 to 1450, which is the width of the image. Now we are going to look to the rotation. Rotation is meaning we just create a new image and we copy pixels from the original image into the new image, applying a degree rotation angle and optional sorry, I forgot. And scale rate if you want to as well scale the image. So you can do both operations at the same time using obviously the library, the class get rotation matrix 2D from OpenCV. So the parameters of this class are the point, the central point that you want to use to do the rotation, the angle of the rotation, and the third parameter is the rate of scale, the scale rate. Okay, so here you have an example. We are going to take the central point of the image. So some point here, we calculate the central point. The central point is just simply take the height and the width, and we divide it by 2 without rest, and then on we get the pixel in the center of the image. Then on we apply the degree, and this is the scale rate. So what I find is just a transformation which give the form I give you here. You had on the documentation what is the affine transformation, that is just keeping the shape and the spaces in between objects of the image. So just simply means that you apply a linear rotation to the image. No, it's not only use this transformation, this methodology to do transformation is applied to other tags in images, but here on a rotation means that you will take an object, you will not you just will simply move in one direction all the image all together, keeping the space in between the different elements of the object rotated. Here we are going to rotate the whole image, so meaning that the spaces, the shape of the objects, everything will be exactly the same. There is other transformations which are deformating the image in some way, but this kind of transformations affine is they are keeping the shape and the spaces in between the different objects in the image. Take a look later to the documentation and you can go through and understand how this is essentially done. But what I want to tell you is in a rotation, what you do, as I mentioned you, is you just take the original image, you create a new image with the same height and dimension, width and height, and you translate pixel by pixel. You translate the location of the pixel into the new image. Just you apply the calculations. So you take the center. So you take the rotation point. You take the angle, and you calculate which is the location of the new image. If you are not applying ratio, scale ratio, it's just copying the information of the pixel in the new locations after apply the rotation. If you do a scale down or a scale up, you need to do the same. You apply you calculate the new location, but in these calculations you need to consider if you are increasing the image, increasing the size of the image, or decreasing the size of the image. At the end, what you get is per every single pixel. For every single pixel, you get a new location in the image, and there is two possibilities. That the location is inside the matrix, so you had in the rotation, you create a image, a new matrix with the same height and the same width, and once you do the transformation and you get the new location can be inside the matrix or outside the matrix, meaning that it is inside the matrix. Let's explain it a little. So the new matrix in this case is something that here we don't see completely. We just see what is I will say overlapping in with the matrix of the original image, and then on. When you do the rotation, the pixels that fall inside the overlapping area that results of overlap the new rotated image in top of the original image. This for these pixels we copy exactly the same information that you have in the original pixels, which means that, for example, this pixel here in this area, so this comes from the original image, and as they are in the overlapping area of the two of the original image and the rotated image, the data is copied. It's not in the location of the new if the location in the rotated image is falling outside the matrix or the dimensions of the matrix of the original matrix, the pixel is ignored, as you can see here. And obviously the new image that you are creating is an image in black and white, like you see here, and only you see in the final image, in the final rotated image, only the pixels copied from the original image which are in the overlapping area of the two images. And this is the effect that you can see here. So again, two possibilities. First of all, you create the rotated image, same dimensions to the same dimension to the original image. You calculate the new locations after using the rotation point and the angle, and if the new location fall inside the overlapping area, you copy the values. And obviously, as is simply a copy, you will see the same color of that pixel in the new location. If the pixel falls outside the overlapping area, either it is inside of the original of the matrix, it is inside of the matrix, it will be black because you don't change it, you don't copy anything in top of that, or is outside of the image, like if these pixels that you have here, that we don't see it obviously because they fall outside, the location of those pieces fall outside of the matrix. Here you have an example here, the same, but we increase the scale of the image. We increase to 2, and then on here we do a rotation of 90 degrees, minus 90 degrees, and we use as well the center of the image. And then in this case, as we are increasing the resolution, we fill the whole original area, and you can see that the image is missing some parts. If you look at the original image, we are missing probably practically some part of the sky. We are just focusing in this area of the image once we have rotated this in this way. Okay. Now we are here changing to an arbitrary point in the image. We take as a rotation point the 10. That 10 will be something like here. We rotate 45 degrees and we don't change the aspect. And you can see here that plenty of the original image had fall outside the image. The rest is black because it's the initial steps creating the rotated image full of black pixels. And here just simply we are using another tool IM utils, we simply do exactly the same as OpenCV, but well, it's another tool that you know to do exactly the same. Here, just we are rotating 160 degrees, and you can see that the image is we are doing exactly the same. And well, that's pretty much all. Is at the end, what we are doing here is just working with a matrix of numbers, and then on we apply simple geometrical operations on geometrical translations of these matrices of numbers, and then on they are pretty simple under the hood. Probably when you start with computer vision and you say how you can do these rotations, at the end it's just if you understand NumPy or you understand how it works under the hood, the operations with NumPy, how to work with matrices, it's very simple to understand what's going on in this. A little bit more complicated is understand the mathematical fundamentals of these transformations and how you calculate the next the final location of a dot once you are rotating with an angle using different. But well, it's just simply applying a formula. You get a location, and here is pretty simple. It is inside the matrix. You copy the pixel information. It is outside the matrix. You don't copy, and the rest is black because you create a canvas in black color, and you just translate the information of the pixels that fall in the overlapping area. Tan simple than that. Okay, and that's pretty much all. Thank you very much for watching the video up to this point. I hope that you found it interesting and useful for your job, for your training, for whatever reason are you watching this video. And if so, just give me a like, subscribe to the channel if you are not already subscribed, and make comments, share with your friends and colleagues, and this way you help me to grow YouTube. Thank you very much, and see you soon.